Okay, so now we're gonna actually talk about block cipher modes of operation, and we're gonna start with the ECB mode because it's the most obvious one. So we said, okay, block ciphers work on blocks of data, and if the data is shorter, we're gonna pad, but actually most likely you would want to encrypt more than 16 bytes of data, right, if you use AES. So what do we actually do if we have more than 16 bytes to encrypt? Well, an obvious solution would be to just chunk up our data, our plain text, into 16-byte chunks, then pad the last chunk, use the padding here, and then encrypt it. This is called the electronic codebook mode, and it's a very bad idea. You should never in your project use ECB. One reason is, well, if we use the same key here, same plain text will be translated to the same ciphertext. So patterns in your plain text will be reflected in the ciphertext. There's a nice image about this on Wikipedia. So if the picture is just well aligned, let's say, you can still, seeing the only ciphertext, kind of see what the underlying structure of the plain text is. In this case, we can even see that this is a tux image that was encrypted. So patterns are transferred from plain text to ciphertext, which is something we really don't want, and which is the main reason why you shouldn't be using ECB. Unfortunately, you see it in practice, for example, in surveillance software used by Germany. So what could go wrong if we use ECB other than patterns? Well, imagine, since we've been looking at web, we're gonna look at it from this perspective. Imagine you have a session that is implemented like this. You have a session with a username, and says if the username is admin, it's 0, and the description, which doesn't matter. Then we encrypt this information with an unknown key for the user, and then store it in a cookie and give it to the user. Now the user can't see what's inside, obviously, because it's AES encrypted. But maybe the user plays around and kind of gets an understanding by error messages, for example, what is inside of this encrypted cookie. So we've used ECB, so these blocks were encrypted to these ciphertext blocks. So as a user, we only see these ciphertexts here, but the server, once decrypted, sees this information. So now, assuming we maybe know what is in the cookie because it's open source, let's say, the code, what could we do? Maybe take a moment and think about it. Well, what we could do is, for example, do ECB block shuffling. We could just take this block here and move it here, so that this block is essentially replaced with this block. Now we send this to the server, and the server will decrypt it because it knows the key. And what this JSON object would then say is username, blah, 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 user admin, username, the string here. Now this is valid JSON. And as you have seen in the past with type juggling, it is very likely that the user admin value will be considered true because we put a non-empty string in it. So just by reordering encrypted blocks, we have changed the plain text even though we didn't have the key. Another common thing is, imagine we have an oracle that encrypts user input and suffixes it with input that we do not know. So we essentially send user input, secret data will be appended to the user input, and we then get the encryption of our user input and the secret data with an unknown key. Well, what can we do if we don't know the key? Well, we could use this oracle to just decrypt the unknown suffixed information. So what we could do, for example, is we submit our user data, or in this case we just submit XXXBB and then ACE, and we choose our user data so that it fills the AES blocks but leaves space in the last of our user controlled blocks for data of the secret information. So what would happen is the computer would chunk up the data in 16-byte blocks, and in this block here, in this block, 1 byte is actually of the secret data, not of the user supplied data. So since we have this block now, the encryption of this block, we can just try out all 256 different values of the last plaintext byte and always submit it to our oracle. And once we have found the correct byte value here, in this case S, the oracle will return the encryption of this plaintext block, which will be equivalent to this plaintext block. So we have now learned 1 byte of the secret plaintext that we weren't supposed to be able to see. Since we don't now know this byte, we can, of course, in the next step just submit a block with A, and then there's space for 2 unknown bytes. The first byte will be an S. Here there will be the S sliding in, and then we repeat the attack for the last byte and then therefore recover the E, and we can repeat this process and just recover all of the secret information that was appended to our user-controlled input. I stole this image from this website, by the way, that you can visit in case you want to read up more on this type of attack.